Hello, Calculus AB. It's Mrs. Jarosik. I'm back again with section 5.6 called U Substitution. So a lot of today will be a lot of just method of how to take an integral when we don't know any other method to take an integral. So when I say that, so far power rule and memorizing your integrals of trig functions, as well as some of the other special functions like e to the x, as well as ln x, or I should say ln x is always a calculator question, or 1 over x. These are problems where when you look at them, we don't have a specific product rule for integrals. We don't have a specific quotient rule for integrals. So there does have to be another way to be able to calculate problems. So that's what section 5.6 really gets us to, is a final method that is very useful when we are faced with integral problems that we cannot necessarily do with all of the methods we've already learned. Okay. All right, so let's get started. I am actually going to take a little time with the warm-up today. So let's go ahead and we'll do the first warm-up together, and then maybe I'll pause it, let you do the other 3 problems and come back and check your answers, okay? So this is a typical, I guess, problem that has to do with problem 1. It's a definite integral. We have a lower bound and an upper bound. This lends itself perfectly to fundamental theorem part 2, right? Our procedure in fundamental theorem part 2. So we first need to actually take the antiderivative. I might want to rewrite first, which I think I'll do that first. Right? That's our rewrite. So now I'll take the antiderivative of x to the -2. So when you add 1, -1, and if you were to divide by 1, you'd have a negative in front. So we're going to evaluate that from 1 to 4. And what we end up with is negative, right? 4, -1, minus, right? And then we have minus 1 to the -1. Okay. What you could also do from here, we could have also just written this as that instead, which may have been a little bit more straightforward, I guess, when plugging in. However, we've now started it this way. This would still be -1. Right. So -1/4 plus 1 is +3/4. Okay, so we have our first answer. So I will start problem 2 with you. Since it's a trig 1, let's do a quick refresher on our trig problems, right? Never a bad idea. So we'll go to the trig 1 together, and then maybe 3 and 4. We will pause and let you work. Okay, so 2 cosine x dx from pi over 3 to pi. We're calculating the integral. Again, fundamental theorem part 2 at play. So we don't have to rewrite anything. We just have to recall our trig integrals that we should have memorized at this point, right? So the antiderivative of cosine is sine. Okay. And now we need to just plug in upper bound and subtract, plugging in the lower bound. Sine of pi is 0. And sine of pi over 3. Okay, unit circle, right? Pi over 3 is a 60-degree angle. Your cosine is 1/2. Your sine is rad 3 over 2. It's positive. It's in the first quadrant. So we have 0 minus √3, which gives us a final answer of -√3. Okay. All right. So we are going to pause, finish the other 2, and we'll be right back with the answers. Okay, we're back. Go ahead and check your two answers. If you need to pause and look at some of the work that I have shown, feel free to do that. And again, problem 5 is also a warm-up question. If you did also do those two before you came back to the video, I did want to talk through those just a little bit. It's a nice review on your properties. So now you're given some information about integrals. 0 to 10 on g of x dx is 20, and 8 to 10 g of x dx is 50. So you have those two integrals given to you, and you are to find the integral from 0 to 8 g of x dx. Okay, well, that is right there a very good example of a problem where we want to use our properties of integrals. So we have a complete area of 0 to 10, and then we have an area defined by just 8 to 10. So we basically need to take this area and subtract that area. So again, I'm going to write out what I'm doing as far as my calculation. Right, I'm actually going to do this. So that would mean it is 20 minus 50, which would give us negative 30. Okay. And then for part B, again, utilizing the properties may make it a little bit more straightforward, but the part that's probably most confusing about this last is that last constant, the net minus 3. We tend to forget that we have to actually take the integral of that as well. Okay, so I'm going to actually split this up. I'm going to split it up into a difference of two integrals. So 2 gx dx minus 3 dx. And so I actually could take, and I'm going to just do that in this step. Let's put the 2 out front. How about that? Okay. All right. So this is pretty straightforward because 0 to 10 is given to us right here. So that's 2 times 20. Not too bad. Minus, now we actually do have to take the antiderivative of that. Minus 3x evaluated from 0 to 10. So we have 40 minus, now this would be 3 times 10 minus 3 times 0, right? So it's 40 minus 30, which is 10. Remember that when you have a constant that you are taking the integral of, think of it as a rectangular region that is going to have, right? You would be taking the 3 itself, or whatever value the constant is, and multiplying it by the difference between your bounds. Okay, so some of you may be doing it in that manner where you didn't have to split it up with the properties, but splitting it up with the properties sometimes keeps you from forgetting to actually take the integral of it, because a lot of people will take 40 minus 3 and then get 37 is their answer, which would be incorrect. Okay, just be careful with those. Okay, here we go. We're going to actually do some U substitution right off the bat. I particularly lay out the notes in this manner because showing a bunch of steps before doing the actual problem can sometimes be it can be more confusing. So I'd like to actually just show you the process. It is repetitive. I will show you for some things that you need to be looking for specifically when you see a problem, like how do I know when to use U substitution? After some practice, it should be pretty obvious when you're going to need it, because when you look at the problem, there shouldn't be any other way around getting to the answer, okay? So 2 things to note before we start. Right now, we are doing problems that are not definite integrals. All of these answers will require a plus C because these are all indefinite integrals. All right, so just make note of that. Okay, we need a plus C on all of these 4 problems in particular. Okay, Now, I had said at the beginning of the video, the reason we need U substitution is because a lot of times we don't have another method. So when I say we don't have another method, we don't specifically have a product rule for integrals or a quotient rule. So if you look at this, unless you want to sit here right now and multiply out x squared minus 5 to the fourth power, which I don't think any of us want to do, and then distribute 2x through that, we really don't have a method for this problem to get to the final answer. This is set up specifically for U substitution. Now, I know that because I've done a lot of U substitution problems. What I'm going to show you is how I know that. What we would be looking for with our process is this. If I tell you that at some point you're going to have to take either this piece or this piece as our first step in U substitution, and actually what you're going to do is take that portion's derivative to make a substitution with. Let's look at these two. If I took the derivative of 2x and got 2, can I actually replace, I guess I should say, can I replace anything in here with that expression of 2? No, that doesn't do me any good if I'm looking at this, right? How about if I look at my x squared minus 5 portion? If I take the derivative of x squared minus 5, guess what I get? I get 2x. What else is in my problem? 2x. Okay, so with our U substitution process, we are always going to be looking for some expression within the problem to take the derivative of to replace something else in the problem. Okay, now I could also say to you that it's more often than not the inside function. So we've talked inside and outside functions, especially with composition before. So if we look at the same exact problem, this is my inside function, right? And that is the one that we determined, we determined that we are going to take the derivative of, okay? If we go right down below to 8, before I start doing any more of the process, let's look at problem 8. Again, you've got squared times something with a square root over it. Again, product rule, we don't have anything like that. Much more complicated looking than previous problems we've done. Let's see if U substitution is going to help in some manner, okay? So if I think about, right, the square root function itself and this specific expression, that specific expression is inside the square root function. So if I were to take its derivative, so if I take 2x cubed minus 4 and took its derivative, it's not perfect, but I get 6x squared. And what you need to notice about that is the x squared part, because it is right here. Okay. With a little manipulation, we will be able to use U substitution. Okay. All right. I'm erasing because we're going to do all of these problems using the thorough method. I just want you to notice some things. Why are we using U substitution for these problems? And again, if we go to 9 and just look at 9 briefly, we have a 2x minus 3, and then our inside function right here is x squared minus 3x plus 1. If I look at that, x squared minus 3x minus 1, and some of you who are very in tune with picking up patterns and picking up things that you're supposed to find in problems, you may already be saying, well, we have to use the x squared minus 3x plus 1, because when you take its derivative, you get exactly 2x minus 3, right? That is exactly what you get when you take the derivative of this, which would then be the replacement for that. Okay. All right. So I'm going to now start the process. If you've already looked or flipped through the pages, you already know that there's the steps to actually completing a U substitution problem on the next page. Again, I just kind of want to go through problems to sort of lead you in that direction. Okay. Believe it or not, I'm going to do 7 probably either last or second to last, because you have an option with 7 to use U substitution or to not use U substitution. 7 is one of those rare problems where you may or may not need U substitution, depending on how comfortable you feel with a problem like that. Okay, let's start with 6. All right, here we go. So we've already talked about possibly using your inside function to help you out. And so if it's a substitution and we call it U substitution, the expression we're going to use to take the derivative of is our U expression. Okay. So usually I do my work off to the side on these problems where I'm going to set up my expression that I am naming U. And we've talked about that usually being the inside function. So if I'm going to call U x squared minus 5, and if I want to take its derivative, so if I'm going to actually go ahead and take my derivative with respect to x of u, right, du dx, I will get du equals 2x dx. Okay. All right. I took the derivative of both sides with respect to, okay. So the derivative 2x dx, what we need to now do is look in our original problem and see if there is a replacement, a substitution that needs to be made or can be made. So if I look back at my original problem, what do I see standing right, or sitting, I should say, standing right here? 2x dx, right in the problem. That means my entire 2x dx expression is going to come out and become a du entirely. Those two things are now coming out. My u expression is x squared minus 5. So this will come out and I will put a u in right there. So basically what I'm going to have is u to the 4th. And then for this entire 2x dx, it's replaced with du. Okay, so what I'm going to do is actually rewrite it neater, okay, with an integral symbol. I haven't taken an integral of anything. What we're trying to do is take our complicated expression that we're supposed to take the integral of and make it a lot simpler so we can take the integral of it, okay? So again, our inside function was x squared minus 5, and I'd say 95% of the time, that will be the expression that becomes u, okay? And we are going to take its derivative. So if we take the derivative, du is equal to 2x dx. Du is equal to 2x dx, and then we can replace, okay? Leaving us with an expression, integral of u to the 4th times du. So now when I take with respect to du, right, my variables agree, u and du. So now I can go ahead and actually calculate this. What's the derivative of something to the 4th power? It's power rule. So u to the 5th divided by 5 plus c. And what do we do in the end? We replace u with its expression. So that means I'm going to go back to my u expression and I'm going to plug it back into the problem. So I'm actually going to, so I can contain some space here. So when I plug that back in, x squared minus 5 to the 4th over 5 plus c. I guess this is probably better. And I will, instead of cramming it all in the little space that I had. Final answer. Okay. All right. Let's go go to 8. I'm going to go back to 7 maybe after the next one. Actually, you know what I'm going to do? I'm going to do these a little bit out of order. Since 9 is the most straightforward, believe it or not, in comparison to problem 6, because with 8, when we were going through it the first time around, remember I said that we might have to do a little bit of manipulation because we got 6x squared with the derivative. Okay, so let's go with 9, because 9 we don't actually have to do anything with outside of picking out what u is supposed to be and then moving on from there. Okay, so again, do we have an inside function? We certainly do. I'm thinking to myself, can I take the derivative of x squared minus 3x and do something with that to move myself in the process? Yes, I can. We said that was 2x minus 3. I have 2x minus 3. I think I'm good to go. So I'm going to start my process. U equals x squared minus 3x plus 1. Du would then be 2x minus 3 dx. So this right here becomes that. Okay. So what we will be doing then is we now have a rewrite of, definitely the bottom is u cubed, right? U cubed. The top, can make that a 1, and we can make this the du. What could you also do? You could also just put du right in the top. But I think what we're most used to seeing is the du or the dx or whatever it is off to the side. So I'm going to go with my original one here, du there. Okay. That's our rewrite. Now, I still have to take the antiderivative of this. So when I do that, I may want actually a rewrite. I would normally want to rewrite this as u to the negative 3 du. Okay. And then when I go to take the antiderivative, this is power rule. So I'd add 1, u to the negative 2, and I would divide by that new exponent, negative 2, plus c. Now I just need to make my substitution. I might bring that negative 1/2 out front. My, actually, let's do this. If I were to rewrite this as, so the negative 2, negative can come out front. 2 stays in the bottom. The u squared will meet it in the bottom. Does that make sense? If I rewrote that first. So then when I go to plug in, I'm already set up for my final answer, plus c. Okay. Okay. All right. Now I actually think I'm going to go to 7 before I even do 8. So with 7, I said that you may or may not need U substitution. So I'm going to approach it without U substitution, because if you're already thinking to yourself, my outside function would be cosine. You're absolutely right. My inside function is 2x minus 1. There's probably not a lot I can do with this. And yes, it does seem like it's very confusing with initially trying to think through U substitution. So the reason you don't necessarily need U substitution for this problem is because of this. Do you know the antiderivative of cosine? Yes, you do. You know that it is sine. Do you know that when you usually take an antiderivative of something that's an inside function for basic problems, that we would divide by that coefficient in front? Yes, you do. And we've probably already done, I'm saying that because we pre-make these videos. So we should have been faced with a problem prior to this video being made, where we may have actually done a problem similar to this, where we're taking the antiderivative of a trig function that doesn't necessarily just have x. that we're taking the trig function of. So when you look at this, we treat this like any other problem. And some of you may already be, I already know what the antiderivative of this is. Why do we need a special method? Okay, and you're right, you don't actually need a special method. Sine of 2x minus 1 divided by 2, because you're dividing by whatever the derivative of that inside function is. And we need the plus c because it's an indefinite integral. Okay. So I'm going to do this also using U substitution so that you can see how the method would work in a problem like this. You only have one inside function. That's the good news. So you don't have a lot to choose from, right? 2x minus 1 is the inside function. All right. So if I'm going to use U substitution, I'll do that over here. U equals 2x minus 1. All right. So I'm going to use the process, right? Du would be then 2 dx. Well, then what does that do for us? Not a whole lot, but if we want to just isolate dx on the right side, because we have dx right here, and looks like that's going to be our replacement. Well, I would have to divide both sides by 2. So that means 1/2 du equals dx. Okay, so how does the replacement work then? So what I'll do is, I'm going to get rid of that. Let me make it a brighter color. So I'm going to continue my work over here. Okay, so when I go to replace, I have 1/2 du. So in replacing dx, so what I'll do is I'll put the 1/2 out front. It's a constant. I have the du right here where I normally put it. It's going to be right next to my new integral expression. And I have a u of 2x minus 1. So that is being replaced, right? So I have u in the parentheses, and cosine is staying cosine. So now I'm taking the antiderivative of cosine u. Okay, we know what that is. It's sine, right? So let's just start my work. I have the 1/2, my constant out front stays my constant, sine of u, right, plus c. Does everybody see how it's going to be the same answer? And we go to 1/2, and this if I pulled out, right, so we pulled out the 2, pull out the 1/2, I should say, out front, it would be a 1/2 here if I wanted that out front. So 1/2 sine, do my replacement, 2x minus 1 plus c. So you can use substitution or not on that problem. Okay. And then finally 8. For 8, we have the inside function of 2x cubed minus 4. Okay. We had talked about that, so I'm going to go straight to setting my problem up. I need du, which is 6x squared, dx. All right. The only problem I need, or the only part of this I need, is the x squared dx, right? Because that's my x squared dx. I need to, if you will, do something with the 6. So what that means is I'm going to, let me get rid of some of my underlining here for myself so that I can, when I divide by 6, I have 1/6 du is equal to x squared dx. There is my replacement outright. Okay. So again, when I have this, I had to divide to manipulate so that my replacement is exactly what I need it to be. I am going to, again, bring that out front of the integral. I'm going to make it a constant in front of the integral. Okay, here go my replacements, and I'm going to put the du at the end. Okay, so x squared dx completely replaced by the du. So the only piece I need to worry about now is that 2x cubed minus 4 underneath the radical symbol, the square root symbol. Well, the square root symbol we didn't get rid of at all. We just got the 2x cubed minus 4 equal to the u expression. So this is the square root of u du. And okay. Now, square root of u, and I think what I'll do with this is move that up a touch for myself and do this. You know what I'm going to say. I'm going to rewrite it before I use power rule. Okay. So now I have 1/6. And then when we use power rule, 1/2 plus 1 would be 3/2. Hopefully we've done some practice with these, right? So that when you divide by 3/2, you're multiplying by 2/3. And of course we have our plus c. Okay. Maybe do a little simplifying. So that would be a 3, that would be a 1. So what would I have? 1/9 u to the 3/2 plus c. And then I have to plug the u back in. So 1/9 u is 2x cubed minus 4 to the 3/2 plus c. Okay. All right. So for some reason, my answer here, I undid that, right? Okay. So that in a nutshell is U substitution. So on this next page, we have lots of practice we can do together. This at the top, very important, some quick refreshers on some of our integral, special integrals that we've already been working with. So just reminders, definitely memorize those. And then here are the steps that we just went through. Okay. Set an expression equal to u, look for parentheses or radicals. And I was calling them inside functions, right? That's what I like to call them, inside functions. Find du, differentiate both sides of your u equation. Substitute into original problem and fix any constants. So that was that if I have to divide by something to make it exactly what I need. Integrate using one of 5 formulas above, right? So what we end up doing when we use U substitution is something that we are familiar with, meaning we're bringing it to a method we already know, and then substitute back to an expression for x, okay? All right, so what I'm going to do is I am going to pause and see how we do on the first example, maybe the first and the second example, and then we'll come back and do the third one together, okay? So I'm going to pause, go ahead and do examples 1 and 2, and then we'll come back. Okay, we're back. So my 2 answers are here. So example 2 was still a little bit different than the ones we've done. So what I did, there's 2 methods you could actually have used with this. And when I say 2 methods, it's still U substitution, but 2 approaches. So example 1, pause and look at my work. If you're not agreeing with what I did, just make sure that you remember that when you take the antiderivative of sine, it is negative cosine. But for 2, again, my original approach was actually slightly different than the one I did. But what I would suggest on the second example is that you, if ever you're faced with, and when I say this, a constant that you can bring out front, that is probably the best habit to form. So I have this 2x squared in the top. That 2 can be brought out front of the entire integral, which is what I did before I started. And then it becomes a lot more like the other 2 problems we had already done, and actually this one as well, where when you're left with something that you don't necessarily have use for, like the 2 did not play a role, we just need dx, right? So we divide by 2. You end up in the same position. You just need x squared dx once the 2 has been moved in front. So you would divide by the 3. Okay. And I'm hoping that that is probably the way most of you did this. However, really quickly, I do want to show that if you went straight from here and you made, you did make your u x cubed plus 1, meaning you didn't move anything. Your problem looks exactly the way it started. And you do this and you say, okay, that's not that's not a 2, right? You look at this, clearly it's not a 2. Could you still make it a 2? You absolutely could. How would you have to treat your multiplication or division in order to make your 3 into a 2? You'd have to multiply both sides of the equation by 2/3. It's a little bit more of a stretch as far as like, okay, wait, what am I doing here? But if you do that, you end up exactly with 2x squared dx on this side, and you'd end up with your 2/3 du. It still works. And notice that at some point in your problem, that's your expression that you've rewritten, and it has a 2/3 out front. So you're going to still get the correct answer. And you do not have to worry. And I'm going to go, since it's 1 over the square root of u, I'm going to go right to the rewrite since we've already been through that. So this would still be u to the negative 1/2. So at this point, your two expressions are identical to each other. Okay, and you can finish the problem then that way. Okay, it's a great problem. Plus C still, because we are still on indefinite integral mode. We will move into definite shortly. All right, so with that next one with E, let's do that one as well. Okay, why don't you go ahead and give it a try? I do have one comment to make before I pause. There is definitely an inside function to this problem. Okay, it's not offset in parentheses, but if I did this for you right now, you have an inside function. Okay, all right, so I am going to pause. Let's see how you do. Okay, we're back. So the one comment I will make is if, as we move through some of these processes a little bit more and you've done more and more of these problems, a problem like example 3, some of you may get to the point where you will be able to possibly do that without U substitution, but even I would probably attempt, or not, I should say, not attempt without U substitution on a problem like that for fear of making a minor error. Okay, so we're going to stick to you have to use U substitution on something like that. Okay, so I set up u is x squared minus 1, du is 2x dx. I don't need the 2, right? So I have to divide by 2. And so my 1/2 du, I brought the half out front of my integral, right? And then I'm just left with e to the u du, which is a nice, easy integral to calculate because it's itself again. And then I replaced my u in the end. Okay. All right. So we're going to do 4. I'm not going to do 5. You can do 5 on your own and check your answer on against the key, or, maybe your teacher will want to do it in class. But I definitely want to get into definite integrals. So we'll do 4 for sure. All right, problem 4. 3 over 4 minus 2x. If I were to do this, so there's a constant, right? And when you see it or recognize it, it's probably easiest to bring it out front. Okay, so if 3 comes out front, 1 over something is always reminiscent of what? Your natural log antiderivative. So if I go back up here, let's see if it's here. 1 over something, right? There you go. So we know we have natural log. You can actually just do this without U substitution. You can. You can do it without U substitution. How would that work? Well, you would need to do ln of 4 minus 2x, but then what you have to remember is that you have chain rule that's applying, okay? The problem with, I should say, reverse chain rule is applying. So if you're very organized and can keep all of that straight in your head, you won't forget to do the chain rule portion of the problem. What I fear is a lot of times if you end up with just writing something like this, that is not correct. That is not a complete problem. You cannot forget that that would require, that term in there requires something to be done. So the chain rule on that is -2. And since we're taking an antiderivative, we would need to divide by -2. So we are going to, right? So if you did this and divided by -2, you're on the right track. Okay, so your final answer, it's a little bit strange to have put the, sorry. Right, so you'd have -3/2 ln of absolute value of 4 minus 2x plus c. That is your final answer. It is the key to this one would be not forgetting dividing by -2. So let's do this one using U substitution, and again, keeps us from having to forget that piece. So if I go to U is going to be equal to 4 minus 2x, du is equal to -2 dx. And again, by saying I only need dx, I don't need the -2 part. That's where you're not forgetting your chain rule, because when you divide by -2, you've already taken care of that. So there's your piece of -1/2 where you're not going to forget. So in your rewrite, 1 over u du. And the antiderivative of 1 over u is ln, absolute value of u, plus c with your 3 out front. And when I rewrote it, I apologize. This should have been rewritten like this. I forgot my -1/2. I even forgot it when I did it. So I have my -3/2 ln of absolute value 4 minus 2x plus c. Again, the absolute value being key at this point. You need to have that on your final answer. Okay. We talked about that a little bit in the 5-4 videos. All right. So let's go to 6. 6 again is one of those problems that you may or may not feel like you need to use substitution. Okay. But you are welcome to use it. Your u value would be 3x. Since all you need is the dx portion. Now this is your chain rule piece, right? So by doing the u substitution, you do not forget that chain rule, okay? So when I go to rewrite this, sine of u minus cosine of u du with my 1/3 out front. So sine of u is, what's the antiderivative of sine? Negative cosine. And then the antiderivative of cosine 3x is, or excuse me, cosine u is sine u. Okay. So I've got the 1/3 and I've got, so you can distribute the minus sign or take the minus sign out of the function. That might look a little bit cleaner once you're done. Cosine of 3x plus sine of 3x. Like that. Okay. Plus c. plus c. Sorry about that. We are still on antiderivatives. I'm checking that last problem. We are still on indefinite integrals, excuse me. Okay, so what I'd like to do, there isn't a whole lot of difference between the indefinite integrals outside of the fact that you don't need plus c. Now we're going to actually be evaluating. So after we do the U substitution portion of the problem, we're actually going to also plug in bounds and evaluate. All right, so the three components must be the same in the same variable. If we use U substitution with a definite integral, we must also remember to change the limits of integration. So we don't have to change the limits of integration. We can change the limits of integration. So there is a little bit more to the process. We're going to do the first problem using the obvious way that we are going to do, and then I'm going to teach you an alternate way to also approach a definite integral with U substitution. Okay, so let's get started. All rules, same rules apply. I'm looking for the function probably inside that I will be able to take the derivative of in order to do my replacement. So that means u is equal to x squared plus 4, because if I take the derivative of x squared, I'm going to get my 2x, which is right there, 2x dx. Okay. So I can go right to my rewrite. All right, 0 to 1. And I have u cubed du. Right? And when I use power rule on this, I have u to the 4th divided by 4, 0 to 1. Okay. No plus c because I'm actually evaluating. Now, what I would have to do first is I have to plug back in my u value first. Before I start doing anything with it. All right, so that's 1 squared plus 4 over 4 minus 0 squared plus 4 over 4. So that would be 5/4 minus 4/4, which is 1. Oh, look what I did. My apologies. I'm glad I caught it before I got to the very end of the problem. But what I'm going to do right now is, if you all noticed, you're probably saying to yourself while I'm writing furiously, you forgot the 4th. Okay, to the 4th. Here we go. Let's do that over again. 1 squared plus 4 to the 4th over 4 minus 0 squared plus 4 to the 4th over 4. All right, a little bit better. So that's going to be 5 to the 4th over 4 minus 4 to the 4th over 4, correct? Big numbers. 5 to the 4th, 625. 4 to the 4th, 256. No, I'm not that good. I did a little bit of pre-work on this so that I knew what those numbers are, but you should have your calculator next to you in case. But the alternate method to this will keep us from having to deal with numbers so large. Okay. It's not that that's terribly, terribly difficult, but there is an alternate way to approach this so that you don't have to end up doing those larger values. Okay. All right, so this is traditional U substitution with a definite integral. An alternate way to do it. Okay, an alternate way. So alternate. Okay. So what we would start with is, after we've decided what u is, right? U is still x squared plus 4. That's the good news. We are going to take our two bounds that are currently given as 0 and 1 and actually plug them in so that they are going to actually represent, instead of x values, they're going to represent u values. So if I were to plug in 0 is my lower bound. So 0 when plugged in is 4. So my new lower bound would be in terms of u. Right. So what I did was u is equal to 0 squared plus 4, so u is 4 in that case. I do the same thing with the upper bound. Since the upper bound is 1, I can say u is equal to 1 squared plus 4, which gives me 5. It's my new upper bound. Okay. So when I go to do the rewrite, right, the rest of my process is exactly the same. du is still equal to 2x dx. But when I go to do the rewrite, here's what's cool about this. It is still going to be u cubed du, but now my bounds are 4 to 5. So, sorry, I just want to make sure we're, all this is 8, right? This is all 7, excuse me. So once I've done that, what's cool about this is, and I take the antiderivative, u to the 4th over 4 from 4 to 5, I do not have to replace now. I just go straight to 5 to the 4th over 4 minus 4 to the 4th over 4. 625 minus 256 over 4, 369 over 4. So when you change your bounds, that is what this part of the directions right above it was referencing, using an alternate method. Either is absolutely fine. The alternate method comes into play occasionally and will make things easier. And some students, once they learn this alternate method, when we have a definite integral, want to use it all the time. It's going to be a preference. It's going to be a preference idea. Okay. All right. We'll do another one using both. And then I think I'm going to end the video because it's probably getting extremely long. Okay, so since I've set up my notes this way, I'm going to go straight to example 9. Okay, so let's do 9. You can save 8 probably for class. Okay. All right, example 9. We'll do it both methods. Let's see what's going on here. All right. I definitely need U substitution. My inside function is there. So that looks like it's going to be pretty good for my U value. U equals x cubed minus 1. Du would be 3x squared dx. I don't need 3x squared. I just need x squared. Okay. All right. So I'm set up now for either method as far as the du dx part. However, if I'm going to do the alternate method, my new lower bound, if I plug in -1, right? If I take -1 and I plug it in there, I get u is equal to -1 cubed minus 1. So what's -1 minus 1? -2, new lower. And if I plug in 2, 8 minus 1 is 7. Is my new upper bound. Okay. So if you're doing it using the alternate method, okay, I'll just keep going right over here with the alternate method. So that would mean I've got my -2, I've got my 7. X squared dx is all du, right? And so that means I just need e to the u, right? And I have a 1/3 constant that is out front. This is my alternate method. So once I take the antiderivative, I do not have to replace u. I do not have to replace the u value. So I've got 1/3 e to the u being evaluated from -2 to 7. E to the 7 minus e to the -2. E to the 7. And I could do minus 1 over e squared. That's really not making anything look any better. But I can simplify that. Okay. If I were to go back to traditional, let me, maybe I'll change the color up a little bit on that. Just, so the traditional way would keep this as -1 and this is 2. The 1/3 e to the u du is going to be the same. However, once I do this, I have to put my e to the x cubed minus 1 back in. And I will wrap this way. So 1/3, that's 8 minus 1, so that's 8 e to the 7th minus, and then -1 minus 1 is e to the -2. Do you end up in the same place? You absolutely do. It is, for some of these problems, a matter of preference. Okay. Now, on this, a problem like 10, which is a multiple choice question, very similar to things that you may see on the AP exam, you are going to be forced to change your bounds. So they are telling you what your U expression should be, and then they want you to pick out which of the following integral expressions is equivalent. So I can tell you right now, under rare circumstances, would your bounds stay the same by using that alternate method? It's not that it can't, it just very rarely happens. So if I start the problem saying, okay, if they're telling me u is 2 sine x, du would then have to be negative, not negative, 2 cosine x. I'm taking the derivative. See, I'm already thinking too much in antiderivative mode. And I've got 2 sine x. So my replacement is simply, I've got 2. I just need cosine x dx though, right? So I need to divide by 2. I do have to do that. Okay. So also with 0 and pi over 2, if I plug in 0, 2 sine of 0 is 0. So my lower bound is staying 0. 2 sine of pi over 2, sine of pi over 2 is 1. So that's going to 2 times 1, which is 2. So my new upper bound is 2. So I have a 0 and a 2. So that automatically eliminates A and B. So my rewrite, I'm just going to go ahead and rewrite it to make it nice and neat for myself. 0 and 2, the 1/2 is out front. And then I've got my cosine x dx, that's all du. And I just need my radical for u. There we go. So which one of those matches? The difference between C and D is forgetting to put the 1/2 out front. So D has to be the answer. Okay. All right. Save the other 2 problems. I think there were only 2 problems, maybe 3 we didn't do for either class time or do on your own, and check against the key. And then you'll get plenty of practice with U substitution in class. My apologies with going on so long, okay? But there are so many things involved in U substitution that I wanted to make sure the video covered as many of the types of problems you may be exposed to, okay? So hopefully you fast forwarded a little bit here and there, tried some of the problems on your own, and then maybe checked against what I was doing if you were getting the hang of it, okay? So we'll see you in class. Have a great day, everybody.